Welcome everybody in a new video. This video will just be a demonstration about how the first and the second Kirchhoff principle work. So I'll just do a little exercise and I'll show you that everything works exactly in the way I have explained you in the last videos. If you still haven't seen them, you can find them in the playlist. Before I begin, I would like to tell you that if you like my videos, you could consider the idea to give me a like or subscribe to my channel, or both. It is just a little effort for you, but it will be very helpful for me. Okay, in this channel I also make videos in Italian and Spanish too, so if you are searching for English only videos, you just have to look in the playlist and there you'll find all the English videos. Okay, let's begin. So, we have this little circuit here. It is very simple. We just have a voltage generator and 3 resistors connected in a series configuration. Okay. The values are the voltage generator has 50 volt, the resistor 1 20 ohm, resistor 2 40 ohm, and the resistor 3 40 ohm. Okay, so what will happen in this circuit? Well, a current will flow in this direction, conventionally speaking. Okay, so we'll have a current flowing in this direction, this conventional direction, because the voltage generator is oriented in this direction, as you can see. And then, when the current flows in this direction, we will have 3 voltage drops. A voltage drop here, another one here, and another one here. Let's call them VR1, VR2, and VR3. So, all these 50 volts here will distribute on these 3 resistors. Let's calculate how much is VR1, VR2, and VR3. Well, the first thing I have to do here is calculate a total resistance, and the total resistance is just R1 plus R2 plus R3. Okay, I just do this. And the result is 100. Okay, so 100 ohm is my total resistance is this in this circuit. Okay. Okay, now if we have the total resistance, we can calculate the current. We just have to do this. The value of our current is just the value of our voltage generator divided for our total resistance. So we just do this. 50 volt divided for 100 ohm. And the result is 0.5 ampere. And this is our current in this circuit, 0.5 ampere. So we have 0.5 ampere circulating here. Now we can calculate VR1, VR2 and VR3. To calculate the voltage drop on a resistance, we just have to multiply the current who flows through that resistance multiplied for the resistance itself. Okay, so the current who flows through R1 multiplied for R1. And what current flows through R1? Well, this current, this same current here. So VR1 is equal to I multiplied for R1. VR2 is equal to I multiplied for R2, and VR3 is equal to I multiplied for R3. We just have to do this. And it is very simple actually, 0.5 ampere multiplied for 20 ohm. Here is 0.5 ampere multiplied for 40 ohm. And here is 0.5 ampere multiplied for still 40 ohm. I do this way and I calculate VR1, VR2 and VR3. Okay, here is 10 volt and here is 20. And here is 20 again. Okay. So now I have demonstrated one thing. If I add all the voltage drops together, VR1 plus VR2 plus VR3, I will obtain a value equal to the value of the voltage generator. So VR1 plus VR2 plus VR3 is equal to, okay, cos 10 plus 20 plus 20 is 50, and this is 50, okay. So I have demonstrated this, and this is the first Kirchhoff principle, the algebraic equation or the algebraic addition of all the tension in a mesh is equal to 0 always, okay. So writing this is equal to writing this. Okay, I just broke this from here to here to this other side, okay? Because as you can see, the direction of these tensions are opposite. This one is oriented in this direction because the plus is in this direction, but these other three are oriented in this other direction. So they are oriented in the voltage drops, and the voltage generator are oriented in opposite directions, okay? As you can see. Obviously writing this one plus this one plus this one minus this is equal to writing, is perfectly equal to writing this. Okay, this equation and this equation are the same, they are equal completely. Why do they have a different sign? Why this is plus and this one are considered minus? Okay, why this one is positive and this other are negative in this case? Well, it doesn't really exist a positive or a negative voltage. It is just about direction. It is just about direction. Remember this. We just decide that this one, for example, is the positive direction, okay? So we begin from here and we decide that this is the positive direction. So beginning from here we write A, okay? Then we encounter this, and this is positioned in the opposite direction. So A positive minus VR1, opposite direction again, minus VR2, opposite direction again, minus VR3, okay? Usually the direction who determines which one is positive and which one is negative is the direction of current, okay? So if the current have this direction, the pieces I encounter positioned in the same direction of current are considered positive. The components I encounter positioned in the opposite direction of current are considered negative, okay? So let's repeat this. Usually we take the current direction as a reference, okay? And whatever we encounter positioned in the same direction of current, we'll consider it positive, and whatever we encounter positioned in the opposite direction of current, we'll consider it negative, okay? So the direction of current is this, okay, this one. A is positioned in the same direction of current, as you can see, this direction, and here this direction, same direction. This one is positive, okay? This one is goes in this tension goes in this direction, while the current goes in this direction, opposite direction, negative. Current goes in this direction, this one goes in this direction, opposite direction, this one is negative in the equation. Okay, so usually you write the Kirchhoff equation this way, the Kirchhoff mesh equation in this way, okay? So you usually write this. And it is the algebraic equation, okay? Because you take in consideration which one is positive, which one is negative, you put all of them together and you will obtain In this case, in the Kirchhoff equation, you'll obtain 0 always as a result. It is also called algebraic sum. Doesn't look like a sum, but it is the algebraic sum. It means that you do this. It is called algebraic sum because you do the algebraic sum. You do this, okay? What you do is you sum each other. You add. It is an addition, okay? You did this plus this plus this plus this. It is a sum, okay? But you consider that this one is negative, okay, and this one too, and this one too. So the result of this sum will be this. Okay, this is why it's called algebraic sum. Okay. Then now let's demonstrate also the second Kirchhoff principle in a very simple way. Let's keep the same circuit, okay? So everything is the same as before. We just add one thing. So this is the same A, 50 volt, this is the same R1, this is the same R2, and this is the same R3. But now we have another resistance, we have R4, and let's say we have also another one, we have also R5, okay? The values are still the same, 50 volt, R1 is 10 ohm, R2 is 40 ohm, R3 is 40 ohm, R4 now is 20, and R5 is 30. Okay, so now we have this situation. It's pretty similar as before, but a little different because we have this other branch here. So what will happen in this circuit? Well, it is very simple. Let's just calculate the total resistance at first. Well, in this case, I have to add this to this, R1 plus R5. Sorry, R4 plus R5. And it is 20 plus 30, the result is 50. Okay, we'll call this resistance RS, series. Resistance is series, equivalent series, okay? We'll call it RS, just this. Then we can redraw our circuit in this way this time. RS here, okay, in place of these other two, because this is equivalent. Here we have R2, and here we have R1 and R3. So now what I will do here is just make the parallel between this and this. So I'll do R2 parallel RS. Okay, this parallel. Let's do it. R2 parallel RS. I will do R2 multiplied for RS divided for R2 plus RS. I will do this. The result is 40 ohm multiplied for 50 ohm divided 40 plus 50. Okay, let's just make it this calculus quickly. The result is 22.2, and we'll call this resistance RP, which means parallel resistance, the equivalent parallel resistance. Okay, Now we can redraw the circuit. We can redraw this circuit in this way. Now the total resistance here is just R1 plus Rp plus R3. And the result is 10 ohm plus 22.2 plus R3 was 40 ohm. The result is, let's write it here, the result is 72.2. Okay, this is our total resistance, and now to calculate the current flows in this direction. We just have to divide this one for the total resistance. Okay, so the current is just let's make this calculus here. 0.69. Okay, almost this. This is our current. Now that we know the current, we can calculate the voltage drops here, here, and here. Okay, we'll have a VR1, VRP, and VR3. VR1 and VR3 will be different now because the current is different, the circuit is different. Okay, let's calculate them. VR1 is equal to I multiplied for R1, and it is 0.69 ampere multiplied for 10 ohm. It is 6.9 volt. Okay, this is VR1. VRP is I multiplied for RP, which is 0.69 ampere multiplied for 22.2 ohm, and the result is 15 point. Okay, this is the result. This is VRP. Now VR3 is I for R3, and the result is 0.69 ampere multiplied for 40 ohm. The result here is 27.6 volt. Okay, so VR1, VRP, and VR3. If I add them together, VR1 plus VRP plus VR3, I will still obtain almost this value, the value of the voltage generator. I'm saying almost because this was not the exact current, it was 0.69 and other numbers, so I will obtain almost this value, but okay, it's still fine, almost this value. So now I got VRP, and I know that when I know the voltage drop on a parallel equivalent, well, this value of voltage drop will not divide into smaller parts on each branch of the parallel. Now, with this value of voltage drop on the equivalent on the parallel, on the total parallel, this value will remain the same in each branches of the parallel. So VRP is equal to VR2 and is equal to VRS. Okay, remember this. VRP here this voltage drop here, this one is equal to VR2. This was the parallel, and is equal to VRS. Okay. So now that I know VR2 and VRS, I can calculate I2, this smaller current, and IS. Because this total current here, the total current who flows here, let's call that it I, this total current flows here, and here it will divide into two smaller parts. The current will divide. The currents divide. The tension does not divide. The tension in a parallel does not divide. The current in a parallel divides. Okay. So this current will divide here into two smaller parts, and to calculate these two smaller parts I just have to, it is very simple, now we'll do it. But then these two smaller parts will unite again here, and here I'll have again this same total current. This is the second Kirchhoff principle, and we'll demonstrate it now. Okay, let's calculate I2 and IS. I2 is equal to VR2 divided for R2. VR2 is okay, is still this value, considering this. So divided for R2, which is 40 ohm. VR2 is, let's calculate it now, 0.38 ampere. Okay, so we have not VR2, we have I2, the current 2. Okay. Now let's calculate IS. Well, IS is VRS divided for RS. VRS is still this. Divided for RS, which is 50 ohm. And the result is still 0.3 almost. Yes, it's 0.306. Okay, almost this. So we have I2 and IS. And now this will demonstrate the second Kirchhoff principle. What does the second Kirchhoff principle say? That the sum of the current who enter in a node is equal to the sum of the currents who exit from this same node. Okay, so in this node, which current or which currents enter in this node? Just one. This is the current who enter in this node. So the sum of the current who enters in this node, which is just this, because it is the only one, it's equal to the sum of the currents who exit from this node. Okay? And what are the currents who exit from this node? These two. I2 and IS are the current who exit from this node. And I is the current who enter in this node. The sum of the current who enter in this node is just I, and the sum of the current who exit from this node are E2 plus IS. So E2 plus IS must be equal to I. Let's do this, let's try. The result will be almost right, but not exactly, because, you know. Well, the result is 0.686 ampere, which is, as you can see, almost the right, almost this. This was I. It is almost this, not exactly, because, you know, the calculus are not perfect, but okay, we can say it is right. Okay. At the same time, this is another node, and the sum of the current who enter in this node, which is I2 plus IS, is equal to the sum of the current who exit from this node, which is just I again. Okay. So we have demonstrated the first and the second Kirchhoff principle in this simple exercise. We can even continue and demonstrate another thing. So we have this current who flows here, but this current here will divide into two smaller parts. Okay, I2, and here IS, as we have said, and here we'll have again this total current I. Okay, so total current I divides into two smaller parts, and here again total current I. Now we can also demonstrate the first Kirchhoff principle again, but in this other mesh here. So we have said that the sum of the tension in a mesh, it is always 0. Okay, so in this mesh we have VR2 oriented in this direction, and then VR4 and VR5. Okay, because we have VRS, but VRS is composed by VR5 and VR4. Let's calculate VR5 and VR4. So VR5 is, you can find VR5 multiplying the current we pass through R5, which is this IS, okay, multiplied for R5, and we'll obtain VR5. IS was 0.306. And R5 was, if I remember good, it was 30. Okay. Well, the result is (9.8). Okay, it is 9. We can say it's 9. And VR4 is the current who passed through R4 multiplied for R4. What current passed through R4? Well, it is still IS. It is still IS. Okay. R4 was 20 ohm. Let's do this. The result is 6.12. Okay, this is the result. So now we have VR5 and VR4. Well, if we consider this electric mesh, and we look at the tensions in this mesh, we have VR2, which is oriented in this direction, and we have VR4 and VR5. If we do the algebraic equation of this mesh, it will be, if we just consider this mesh, you can see this tension is oriented in this direction, and these other two are oriented in this other direction, so opposite direction. The equation of this mesh will be VR2 minus VR4 minus VR5 equals 0, or VR2 equal the first Kirchhoff principle still remains valid in this way. Let's demonstrate it. Okay, so VR2 is how much is it? Okay, so this was VR2, right? 15.3. Okay, let's demonstrate this. or this, they are the same. Okay, let's try this. VR4 is 6.12. Okay, let's write VR5 first. 9 minus VR4 6.12. The result should be 0. It will be not exactly 0, but almost 0. Okay, the result is 0.018. Okay, almost 0. We can consider it as 0. So the first Kirchhoff principle is demonstrated again in this other mesh. So what conclusion we can say at the end of this? Just say a little conclusions, and then for this video is enough. Okay. Well, we have demonstrated that the algebraic equation, the algebraic sum of all tension in a mesh is 0, and this is valid for this mesh, but this is also valid for this other mesh. Okay, so remember this. This will be very useful to write the Kirchhoff equation in the next exercises. We've also demonstrated another thing that, okay, the second Kirchhoff principle, the sum of the current who enter in a node is equal to the sum of the currents who came out from this node. Okay, so this I in this case is equal to I2 plus IS. And the same thing here. I2 and IS enter in this node. The sum of the current who enter in a node is equal to the sum of the current who exit from this node. So I2 plus IS is equal to I in this case again. So we demonstrated the first and the second Kirchhoff principle, and also other things. What other things? Well, we have demonstrated that the Eiger resistance takes more voltage drop, and the smaller resistor take less voltage drop. As you can see, like in this case, for example, the smaller resistance take a smaller amount of voltage drop. The bigger resistance, which is R3, which is 40, take the bigger amount of voltage drop. Also, the behavior of the current, it is exactly the opposite. The current is bigger in the branch with less resistance. So when the current divides in a parallel, we will have more current in the branch with a smaller resistance. So the smaller resistance take more current. Okay. And the Eiger resistance take less current. Okay. So remember this. Current and voltage behave in two opposite ways. In a parallel, the total voltage drop on a parallel does not divide. It still remains the same on each branches of the parallel. This is what the voltage drop on the total parallel do. But the current who flows through a parallel, okay, this total current flows through the whole parallel, okay. The current who flows in the direction of a parallel, well, the current will divide into smaller parts. Okay, so the currents divide in a parallel, the voltage does not divide in a parallel. Okay, but this is different from a series. We have the same voltage drop here and here, okay, but the voltage drop divides on a series. We have a series here, and this voltage drop is equal to this total voltage drop, okay, but this voltage drops divides a smaller part here and a smaller part here. So the voltage drops divides on a series, and the current doesn't on a series. In a parallel, it is the opposite. In a parallel, the voltage drops of the total parallel does not divide, but the current who flows in the direction of this parallel, well, the current will divide inside the parallel. Okay, so remember this. Remember how the currents and the voltage behaves in a circuit. Okay. And what else could I say? I don't think there's much more things to say. I think it is enough for this video. I hope you have understood everything. And if anything is not clear, just tell me in the comments. I'll do everything possible to answer your questions. If they are about electronics. If they are about other things, I don't know. I'll try it, but I don't know if I can. Okay. There was another thing I wanted to say, but I don't remember it now. Okay, maybe for the next videos. For this video is enough. I hope you have understood everything, and okay, see you in the next videos. Bye.